Maths is all about numbers. Everything that you learn in mathematics is nothing but different forms of number pattern. Actually, not just math, but all physical phenomena, natural phenomena, everything can really be explained using number patterns, right? So these number patterns are at the very core of all math or all nature, right? Let's look at a very simple number pattern, right? Let's say 1, 3, 5, 7. What are these? If you look at them, what are they? These are nothing but odd numbers. These are nothing but odd numbers, right? Now you could visualize them as triangles. One triangle, this is 3 triangles. If I divide it further, this will be 5 triangles here, 7 triangles, right? So if I want to divide a triangle into each part, into equal areas, the number of triangles I'll get in each row is going to be an odd number, right? This is one way to visualize it. Now let's add them and see. 1 and 3 you add, you'll get 4. 1 plus 3 plus 5, you'll get 9. 1 plus 3 plus 5 plus 7, you'll get 16, right? What are these? Nothing but square numbers, right? Why do you get square numbers? Because adding triangles gives you squares, right? 2 triangles make up a square, which is why adding these numbers that represented triangles gave you a square. So it's just one way to see it, right? There's another way we can visualize triangles. Let's take 1, then I have 1 and 2, 1, 2 and 3, 1, 2, 3 and 4. These are all triangles, right? The first one has just 1 point, the second one has 3 points, the third one has 6 points, the fourth one has 10 points, right? So we call all of these as triangular numbers, right? We call them as triangular numbers because as you see, they form triangles, right? Now again we said if you add up triangles, you get squares. So if you add these triangles, you should again be getting squares, right? Let's try it. We have 1 first, 1 and 3 gives you 4, 3 and 6 gives you 9, square again. 6 and 10 gives you 16, square again, right? So you get these square numbers. These are nothing but square numbers, right? 1, 4, 9, 16 are nothing but square numbers, right? You can see that in the figure also. What we did here, 1 plus 3, so 1 and 3 gave you 4, right? I'm just rotating the triangle and putting it on top. 3 and 6 gives you 9, right? 6 and 10 gives you 16, right? So multiple ways in which you can visualize a simple concept of triangles and squares, right? It actually links numbers, geometry, algebra, everything, right? Which is why number patterns are so fascinating, right? When you start visualizing number patterns, they become extremely fascinating. And this is nothing new for you. You've already been learning number patterns for a very long time now. In fact, what is the very first thing that you learn in maths? It's nothing but a number pattern. The first thing that you learn in maths is nothing but counting, right? 1, 2, 3, 4, 5, 6 and so on. That is nothing but a number pattern, and we also have a name for it. That's natural numbers, and we represent it with n, right? So there are some number patterns that you already know, right? The very basic one, the first thing that you learn in math, what is it? Counting 1, 2, 3, 4, 5, 6 and so on, right? This is actually a number pattern and it also has a name. It's called natural numbers. We normally represent it by n, right? So on a line 1, 2, 3, 4, 5, these are nothing but natural numbers. We can now count everything. Let me take a basket. There's 1 apple here, 3 oranges, 4 fruits in total, right? Now what if we want to represent what is left in the basket, right? We could represent the fruits using natural numbers. How do we represent what is left in the basket? There is nothing, right? There's nothing. How do we show nothing with natural numbers? You can't, right? Which is why we now bring in a 0. Right? If we include 0 to the set of natural numbers that we already had, we now get whole numbers. These 0 to infinity are nothing but whole numbers represented by W, right? Again, there are infinite such numbers. Let's now see what numbers we get by adding 2 whole numbers, right? Say we add 2 and 5. We get 7, which is also a whole number. Try 3 plus 8. That gives you 11. Which is again a whole number, right? So adding whole numbers is still giving us whole numbers, right? So we can still work with this. Now what happens if we subtract these 2 numbers instead, right? We do 3 minus 8. What does that give you? Minus 5. Now minus 5 is not a part of our set of whole numbers. right, is not a part of our set. So what do? To be able to represent minus pi, we add another set of numbers to the left of 0. These are nothing but negatives of the natural numbers, right? So we add negatives of the natural numbers to the other side. This entire set of numbers that we now have is called as integers, right? Represented by I, again an infinite set, right? So, okay, do we now have all the numbers possible? Seems like a lot, right? But not really. Let's zoom into a section of the number line to see. Let's say we zoom into 0 to 1. Can we have more numbers here? This is 1 unit, right? This is 1 unit. Can we divide it into smaller units is the question. If we can, then we would have numbers in between, right? So instead of a section, let's imagine it to be something like a pizza, right? Let's imagine this to be a pizza. Let's move the line down. Let's have a pizza instead of the number, right? Now, can we divide this? Essentially, we want to divide this unit, right? This is 1 unit. We can divide it into 2 halves like this. So between 0 and 1, there is 1 point, which is the half, correct? Now, if we take this half, you can further divide it into 2 quarters. You can further divide it into 2 quarters. What does that tell you? Between this half, there is a point which is the quarter, right? Similarly, this quarter, you can further have a point 1/8. This 1/8, you can have a point 1/16, and so on, right? We can keep going. We can keep slicing it into smaller and smaller pieces, and we can keep dividing our number line, right? So what does that tell us? That integers are not enough to represent all possible numbers there are. In fact, between every 2 integers, there are another infinite set of numbers, right? We were able to divide it infinitely, right? We can keep going on and on, right? So between any 2 integers, there are again an infinite set of numbers. Now these numbers that we just got are called as rational numbers, right? Rational numbers, the definition for these is nothing but any number that can be represented as P by Q, right? P by Q, where P and Q are integers, Q is not 1, and P and Q don't have any common factors, right? So that is essentially what a rational number is. And actually, even all the integers are rational numbers. Why? Because Q can be 1, right? If you put Q equal to 1, they all become integers. So integers are rational numbers, right? Now there are 4 types of numbers that we saw. As you can see here, all natural numbers are whole numbers. All whole numbers are integers. All integers are rational numbers, correct? The converse, however, the reverse of this is not really true. You can move only in one direction, right? Let's take an example to understand why. 3 by 4 is a rational number but not an integer. Minus 3 is an integer but not a whole number. 0 is a whole number but not a natural number, right? Which is why the reverse is not true. Right? So now do we have all the numbers? You'll see that with rational numbers, we'll be able to do all basic mathematical operations and the result would still be a rational number. So we'll be able to describe all the results also using just rational numbers. Try it out. 3 by 4 plus 5 by 2 gives you 13 by 4. 3 by 4 minus 5 by 2 gives you 7 by 4. 3 by 4 into 5 by 2 gives 15 by 8. 3 by 4 divided by 5 by 2 gives 3 by 10. As you can see, the results of all of these operations are rational numbers, right? So it looks like we now have all possible numbers, right? There are an infinite set of integers and infinite numbers between any 2 given integers, right? Infinite set of integers and infinite numbers between any 2 given integers, right? So it looks like we have all possible numbers. And that's what the ancient Greeks thought too. Until one of the Pythagoreans wondered, how do you represent square root of 2? For some reason he was interested in square root of 2. He looked at his number line and he realized that I cannot represent this because there are no 2 numbers P and Q such that square root of 2 is equal to P by Q, right? So he couldn't plot his square root of 2 on this number line. The same was true for the constant pi, right? Pi, which is circumference of circle by diameter. So in your calculations, you've used 22 by 7 as the value of pi, right? That's just for convenience of calculation. That's not really the true value, right? Pi is 3.1415 and goes on and on. Now this, again, cannot be represented as P by Q and hence does not fit onto our number line, right? So these numbers that cannot be represented as P by Q are called as irrational numbers. Interestingly, there are infinite irrational numbers between any two rational numbers. Just as we had an infinite number of rational numbers between any two integers, between any two rational numbers, we again have an infinite number of irrational numbers. Lot of infinities here, right? That's what numbers are, infinite, right? So root 3, root 5, root 6, all of them are irrational numbers, right? And as the name itself suggests, an irrational number is something which is not a rational number, right? So basically, no rational number is an irrational number and no irrational number is a rational number, right? These two are separate, unlike the numbers that we saw so far. So together, if I combine the rational and the irrational numbers, together we get the real numbers, right? So if you combine both of these, the rational and the irrational, you will get the real numbers, right? All of these together are called real numbers. Now let's say we want to plot an irrational number, root 2, on the number line. This question has a set of statements, a set of true or false statements about natural numbers, whole numbers, integers and rational numbers, right? So we know, let's quickly see what natural numbers are. Natural numbers are 1, 2, 3, 4 and so on. Whole numbers are add a 0 there, 0, 1, 2, 3, 4 and so on. Integers are add the negative side as well, so -1, -2, -3, -4 as well. And then rational numbers are any number that can be expressed in the form p by q. So the first question is, every natural number is a whole number. You can see that is clearly true. Every natural number is a whole number, right? Very simple. The second one is every integer is a whole number. Now you can see that's clearly not true. See -2 for example. You see -2 in integers. Is -2 a whole number? You see -2 on the whole number line? No, right? Which means that every integer is not a whole number, right? Some integers are, but every integer is not. So this is false. Now the third statement is every rational number is a whole number. Every rational number is a whole number, right? Is that true? No, right? Because this -2 that you just saw, which was an integer, is also a rational number. I can express it as p by q, right? -2 upon 1. You clearly don't see it on your whole number line, so every rational number is not a whole number, right? If every integer is not a whole number, obviously every rational number cannot be a whole number, right? Because all integers are rational. Similarly, you can check any other point as well. 3 by 4. 3 by 4 is a rational number. You don't see it on the whole number line, right? So very clearly, every rational number is not a. Let's say we want to plot an irrational number root 2 on the number line, right? So far numbers were easy to plot. The rational numbers were easy to plot because we had them in the form p by q. Now we don't. So how do you plot root 2, right? So let's take a number line. The simplest way to plot it is from 0. I'll take 1 unit here, 1 unit this side on the positive side of the number line and 1 unit on top, right? So I have 1 unit here and 1 unit on top. Now what will the length of this diagonal be? What will the length of this diagonal be? This diagonal is nothing but root 2, right? This diagonal is nothing but root 2 simply because of Pythagoras theorem, right? Simply because of Pythagoras theorem. Because if you look at this triangle, in this triangle, one side is 1, the other side is 1, right? So the third side or the hypotenuse will be nothing but square root of 1 plus 1, which is why root 2, correct? Which is why the hypotenuse is root 2. So we got the hypotenuse as root 2. Now take the hypotenuse, just take a compass, right? Keep it on the origin, the other end on hypotenuse, and plot the hypotenuse, right? Keep the radius constant, plot the hypotenuse on the number line. So you have your hypotenuse on the number line. The hypotenuse is nothing but root 2. That means this distance is, right? That's how you will plot root 2 on a number line. Simple using Pythagoras theorem, right? This side is 1, this side is 1, this is root. As simple as that, right? So you have root 2 now plotted on the number. Let's say you now want to plot root 3. How would you do that? For root 3, look at this triangle again, right? We had 1 plus 1, we got 2. If we want 3, how will we get? 2 plus 1 will give us 3, right? And 2 is nothing but root 2 squared, right? So in this same triangle, if I change this side to root 2 and keep this side as 1, then my hypotenuse will be 3. Right? Because root 2 squared is 2 plus 1 squared is 1 will give you